Hello again. In this lecture we are going to revisit our governing differential equations, and this time we are going to include transient effects so that we can have the tools necessary to do transient simulations as opposed to steady state simulations. So our objectives in this particular lecture are to understand the derivation of the transient term of the governing equation, understand the physical mechanisms behind a term called specific storage, which will come into play, and understand the difference between specific storage, storativity, and specific yield, which are some coefficients we use when we do transient modeling. So back when we derived our governing equations for steady state conditions, we had this representative element in the saturated aquifer, dimensions dx, dy, dz, and we looked at mass flow in and mass flow out, and we used an assumption of mass balance, inflow minus outflow equals 0. And the mass flow rate was defined as the mass times the Darcy velocity. And from that, we were able to derive a governing equation that looks like this, assuming that our principal axes of hydraulic conductivity are aligned with the x, y, and z axes. You notice that the term on the right is equal to 0. Well, when we began our derivation of the general equation, we started out with this term, inflow minus outflow equals the change in storage over time plus sources and sinks. And at that time, we addressed the sources and sinks question, which is just a term we call R that we throw on, and mentioned that the storage term would be addressed later. Well, assuming that we have, again, just for the purpose of the derivation, we can throw the sources and sinks back in later. But that term, change in storage over time, represents the change in mass, water mass, stored in the system as a function of time. So let's rederive our governing equation with this storage term on the right. Or more specifically, let's derive this storage term in terms of heads and time and in a manner that we can solve using our normal tools for solving our differential equations. So remember that mass per unit volume can be expressed as density multiplied by the volume of the voids. Okay. So the water is in the void space, and so if we take the density of water and multiply it by the volume of the voids, we have the mass of water in the voids. And the volume of the voids is equal to the porosity N multiplied by the total volume. Remember, porosity is the volume of the voids divided by the total volume. And that is equal to or the total volume in this case, in the context of our representative element, is dx, dy, dz. So therefore, if we want to come up with a term representing the change in storage with respect to time, we can take the derivative of this. It's the change, so the water stored in the soil is the density times the porosity times dx, dy, dz. But dx, dy, dz doesn't change. This density porosity term could potentially change. So it represents the derivative or the rate of change of the density times the porosity with respect to time multiplied by the volume of the representative element. So remember that term. So if we go back to in the steady state case, we had inflow minus outflow equals 0. And at one point in our derivation, we had this equation. Minus the derivative of the mass flow rho Vx in the x direction times del x del y to z, minus the derivative of the mass flow in the y direction and the derivative of the mass flow in the z direction. And at this point, when we were doing our initial derivation, we just divided by dx dy dz and called it good. Well, now, instead of having 0 on the right-hand side, we have inflow minus outflow equals the change in storage over time. And if we plug everything in, we have that the black terms here represent inflow minus outflow, and this item shown in red represents the change in storage over time. And once again, if we divide both sides by dx dy dz, we end up with this term. Now previously we had that same term expression on the left, and on the right it was equal to 0. Well, now we have this derivative on the right, which is with respect to time, and instead of Darcy velocity, it's with respect to the porosity. Now, as was the case before, if the density is constant, we can move it outside the derivative and divide by the derivative, and divide by the density and get rid of it. So now we're down to this equation. And again, that part on the left-hand side is the same thing we had before. And so if we make the same assumptions and continue like we did before, assuming k, the off-diagonal terms is 0, and inserting Darcy's law, we come up with this equation, which is exactly the same as before, except on the right-hand side we have the derivative of the porosity with respect to time. Now let's pause for a second. Now remember that right-hand term represents the change in storage over time. And now we're saying that that's equal to the derivative of the porosity over time. The porosity is the void space in the soil. And remember, we're talking about saturated soil here. So if there is any change in storage in that little element, it can only happen if the porosity changes. The void space changes over time. And so that's a really important insight or consideration as we think about transient modeling. Now, why would the porosity change over time? We'll get into the physics here in a minute, but that is basically what we're trying to come up with. So now what we need to do is somehow relate that porosity term to a change in head, because we need this equation to be in terms of head as we have on the left. We need to do the same thing on the right. And so it turns out, this is what I was saying, so we need to simplify del n del t and write it in terms of head. And it so that term del n del t represents a change in volume due to a change in head. In other words, the porosity changes when the head changes. So as the water level goes up and down, the void space changes. What happens is that void space expands or collapses or compresses. And so we can write that out mathematically like this. The change of porosity with respect to time is equal to this term called specific storage multiplied by the change in head with respect to time. And specific storage is equal to the change in the water volume in this unit space with respect to a change in head. Or, that's what this summary says. So why would that happen? So I have a graphic here to visualize this. And suppose we have a 1 by 1 by 1 or a unit volume of the aquifer. Specific storage is as follows. If you lower the water table by 1 unit, it's the change in water volume stored in that aquifer resulting from that 1 unit head loss. And by 1 unit, I mean, say, 1 meter or 1 foot. Now, why would that happen? We're going to get back to this later in the lecture, but when the head drops a meter, for example, the pore pressure in that water space goes down, and that results in an increase in what we call the effective stress in the aquifer matrix. So it loses a little bit of the buoyancy effect, and it causes the aquifer to compress. So as the pore pressure goes down, the stress on the particles increases, and it compresses slightly. And as it compresses slightly, some water is squeezed out of it. Just think of this cube as a sponge. And if you reduce the water level, it increases the gravitational force on the sponge, and it squeezes it a little bit, and some water comes out. Also, at the same time, as the pore pressure goes down, the water itself expands a little bit, and that also results in some water coming out. So again, the specific storage is the volumetric change in water in a unit volume of the aquifer due to a unit decline in head. So if we put that back in, we end up with this final form of the governing equation, minus the source sink term, which is just minus R or plus R. And again, so we have on the right-hand side, we have a derivative, the change in head with time, and you multiply it by that coefficient, and that converts it to a specific amount of water change versus time. This is sometimes called the diffusion equation, but this is effectively the governing equation that we solve in mod flow. And so now, before I said, well, the solution to this equation is a function describing the change in head spatially, or if you plug in an x, y, and z, it would tell you the head anywhere in the domain. But now we also have a time variable. So we have the head changes spatially throughout the aquifer, but it also changes over time. Say your water table goes up or down over time as a result of different stresses. And then again, if we want to have the final form of this, we include the R term for our sources and sinks, and then that can either be on the left-hand side or the right-hand side. So this, in effect, is the full equation that we solve in mod flow. All right, now let's drill down a little more closely into this specific storage term. We're going to actually derive this specific storage term. A decrease in head infers a decrease in the fluid pore pressure U and an increase in the effective stress of the soil. That's what I talked about before. The water that is released from the aquifer due to a decrease in head is due to two things. Number one, compression of the aquifer due to an increase in the effective stress. Remember, the total stress is equal to the effective stress in the soil plus the pore water pressure. And so if you reduce the pore pressure, you're going to increase the effective stress. And this is controlled by something called the aquifer compressibility. And so the change in water volume is equal to minus the total volume change, which is equal to the compressibility of the aquifer times the volume times the change in effective stress. But remember that we are If we're dealing with a unit volume of the aquifer, then that VT term goes to 1, and we're left with the change in the water volume is equal to the change in effective stress, and the change in effective stress is equal to minus the change in the pore pressure, and the change in the pore pressure is equal to the unit weight of water times the change in head. So if we put this back into our form, we have the change in the volume of the water is equal to minus the compressibility times the unit weight of water times the change in head. And since we are assuming a unit change in head, that DH goes away and the minus sign goes away, and so the change in the volume of water is equal to the compressibility times the unit weight of water. Now there's also, so that's one component. This is the change in the volume of water in the unit volume of the aquifer due to a unit change in head resulting from a change in effective stress. But there's also, as I mentioned before, when the head drops, there's an expansion of the pore water pressure due to a decrease in the pore pressure. And this is controlled by the fluid compressibility beta. So that in this case, there's a change in water volume, which is equal to minus beta times the volume of the water times the change in pore pressure. And the volume of the water is equal to the porosity times the total volume, which is equal to N, because again we're using a unit volume, so the VT is equal to 1. Therefore, if we plug that back in, we get the change in the volume of water is equal to minus beta times N times the change in pore pressure. And for a unit drop in head, or DH equals minus 1, du is equal to gamma water times DH, which is equal to minus gamma water. So if we plug in minus gamma water here for du, we end up with the change in volume of water is equal to beta times the porosity times the unit weight of water. So on the previous, so for impact number 1, the compressibility of the aquifer, we had alpha times gamma water, and for the expansion of pore water due to a decrease in U, we have beta times the porosity times gamma water. If we combine both of those together, we add those together and factor out the gamma water. The specific storage is equal to gamma water, the unit weight of water, times alpha, the compressibility of the soil matrix, plus porosity times beta, the compressibility of the water. And by the way, alpha is equal to 1 over the modulus of elasticity. And the modulus of elasticity is defined as the stress-strain ratio. So in this case, it's upside down. So the little epsilon term there is the strain. So the change in strain is a function of the change in effective stress, where that's strain and that's the modulus of elasticity. And so you can actually look up the modulus of elasticity for just something you can measure in a laboratory or look up for different materials. This alpha term decreases with increasing stiffness. It's like I say, it's the inverse of the stiffness. The modulus of elasticity is a function of the stiffness, and this is the inverse of it. And so there's a famous book on groundwater by Fries and Cherry, and they give a table here. And so based on the soil you have, you can look up a range of values, and these are in meters or meter squared per Newton. And beta is a constant for water equal to 4.4 times 10 to the minus 10th meter squared per Newton. So it's quite small. Water is relatively incompressible. So you can actually, using this table and plugging these terms in, you can calculate, or you can estimate specific storage based on these coefficients, or you can do a field test. There are a number of pump tests you can do in the field, transient pump tests, where you can back calculate your storage coefficients from that. But it's good, I think, to derive that, to understand what's going on. And let's just summarize here before we continue. The transient term we've added to the governing equation relates to the change in water storage over time. And that, we related that to the change in porosity, and the porosity change is due to a change in head. And in a more direct fashion, when the head goes up or down, water, the soil matrix expands or compresses. And that expansion or compression causes the water storage to change with time. And there's a minor effect due to water compressibility, but mostly it's the void space in the soil that's expanding or contracting. Okay, so that concludes the derivation of the general equation of a representative element in the saturated aquifer. And I'm going to stop this video here, and then we'll pick it up with another video that looks at the special case of aerial flow for both confined and unconfined conditions.